All right, so in this video, we're going to be deriving the formula using calculus for the volume of a tetrahedron. And we'll do it for a sort of generic tetrahedron with side length of A, edge of length A, and then for an arbitrary height, okay, H. So normally people think about a regular tetrahedron, which has equilateral triangles on all sides, but you can think about a tetrahedron as just a triangular pyramid. And this pyramid could be very long or very short, it could have different aspect ratios, right? So could maybe a very long one maybe look like something like this, or with different heights, right? Or a very short one, maybe something like this. So we're going to be looking at that. The formulas for those that we're going to be deriving, just so you can see right off the bat. Again, we're going to be using calculus. But the formula, the generic formula, which we'll be deriving, is root 3a squared h over 12. And then for a regular tetrahedron, when you have the Platonic solid, the four equilateral triangles, that formula for a regular tetrahedron is a cubed over 6 root 2. So in this video, we'll be deriving both of those formulas, but really where the calculus comes in is this generic one, and then we're just going to figure out the height for a regular tetrahedron, and that's going to get us to this one. So that's the regular tetrahedron. So let's get started. And so we're using calculus here, and so what we're going to be doing is we're going to be thinking about adding up a bunch of triangles starting from the base, right? And adding up all these triangles that are getting smaller and smaller, right? So we're going to add up all the way to the top. I'm not going to draw all the triangles, but we're going to add up all these triangles until there's no triangle at the apex of the pyramid. And so sort of the starting point for this is to think about that bottom triangle and to think about in calculus what the volume would be. And so it's going to be an integral, and we're going to call it's going to be an integral of all these triangles. So we know the area of triangle is 1/2 base times height. And just for nomenclature, I'm going to use B prime here and H prime. And then the volume of each of these little triangles is going to have an infinitesimally small height, right? So the area is given by 1/2 B prime H prime. That's changing over time, but that height of this little triangular prism, each infinitesimally small triangular prism, that's going to be dx. So that's where the calculus comes in, and then we're going to be adding in all of these different triangles, and so we're going to be integrating from what we'll call x equals 0. We'll define that as being sort of at the bottom of the pyramid, so x equals 0. And then at the apex, we're going to call that the height of the pyramid. And so that I'm going to call h, so not h prime. So you can see, we have the height of the triangle is h prime, and the height of the tetrahedron is going to be called h. So what that means is we're going to be adding up all these triangles, and we're going to be integrating from x equals 0 to the top of the pyramid, x equals 8, so h. So now we have our bounds there. And the next thing to do is to think about how do we get b prime and h prime in terms of a function that has x in it, because we're integrating on dx. And so we need to think about how b prime, the base of the triangle, varies as we're varying this x position. And so first, let's draw out that triangle. Of course, this is an equilateral triangle when we're talking about a tetrahedron at the base. So equal in length with 60 degrees, right? And so the area of that triangle, when we're talking about the base, the area of that triangle is simply going to be equal to A, right, at the base. A is what we would call the length of each vertex. So in the tetrahedron, in a regular tetrahedron, all those edges, sorry, the edges, not vertex, all the edges would be length A. So but at the bottom, even an irregular tetrahedron that's very elongated still will have a base A. So what we can write is at x equals 0, our base is going to equal to A. And then the question is, what is our height going to be? We can also think about, let's think about our base first. So at x equals h at the top, b prime, our base height's going to be 0. So that's quite nice. And then let's do the same thing for h prime and for h. So for h prime, for x equals h. Obviously at x equals h, there's no triangle, so the height of this triangle is going to be 0. But it's a little trickier. We have to do a little bit of math here to figure out what h prime is going to be like at the bottom, right? What is the height of this triangle? We're trying to find the area of this triangle, 1/2 b prime times h prime. So a equals b prime here, and then this is h prime. And so we have a right triangle here to figure out our height, and this is going to be half of our base, so it's a over 2. And then we know that this is also equal to a because it's one of the edges of our tetrahedron. So at that point, what we can just simply do is use the Pythagorean theorem to solve for h prime. So we're going to have a over 2 squared, right? A squared plus b squared equals c squared. So we're going to have a over 2 squared plus h prime squared equals a squared. And if we solve for that, we're going to get a squared minus a squared over 4. And so h prime is going to be equal to 3/4 of a squared. Sorry, h prime squared. And so then what's going to be the square root of that? And so that ends up being root 3a over 2, right? Square root of 4 is 2. So now we can plug in here at x equals 0. We know b prime equals a, and h prime we just figured out is root 3a over 2. All right, so at this point, what we're going to do is we're going to, we have 2 different points, okay? And we know that the area of this triangle, because there's lines here, okay, across the pyramid, that as we go from 0 to h, we're linearly decreasing the area. The base is linearly decreasing as we get to the top of the pyramid, and so is the height. And so what we can use is our favorite expression, y equals mx plus b, right? And here what we're thinking about, we're varying x, that's going from 0 to h, and we're looking at how b prime or h prime varies, so that's our y. So let's think about, b prime first varying with x. And first thing we're gonna do, so we can write b prime equals x plus b, just to be clear here. Let's calculate m. M is our slope, right? So that's going to be rise over run. So that's going to be delta b prime, right? That's our rise, our y value, over delta x. And so what's our B prime? Well, we went from let's say A, right, to 0. So it's A minus 0. And our X went from 0 to H. So 0 minus H. And so we end up with negative A over H. So that's our M. So now we can plug that into our expression up here for M, now that we know our slope. So B prime equals negative A over H plus B. And sorry, I'm running out of room here, so I'm just going to block this portion off, separate ourselves. So now we just have to plug in a point. And so probably the easiest point is to plug in when x equals 0. When x equals 0, B prime is equal to A. So we're going to have B prime equals to A. We plug that in there. Negative A over H times 0 plus B. And so that just tells us that B equals A. And so at this point, we have a nice expression. We figured out what B prime is as a function of x, which is going to help us plug it in up there into our integral. So B prime equals negative A over H x plus A. Okay. And so something very similar is going to happen with our H prime, and so we can do a very similar thing here. I'm just going to rewrite this expression up here. We're running out of some room, and I'm just going to erase some stuff to give me some room. So let's erase all this. Actually, we can save some time here. As you'll see, the form of this expression ends up being, again, very similar. Now we're going to do it for H prime. And again, the height of the triangles that we're adding up as we're going up the tetrahedron, they're linearly decreasing. And so again, we can use equation of a line. And so we can use y equals mx equals b. This is now H prime varying with x, thinking about that. And so we have H prime equals mx plus b. We have m is the rise of the run, so that's going to be delta H prime over delta x. And what is H prime? Well, at one point, it is root 3a over 2. And then at the other point, it was 0, so it's just minus 0 over 0 minus h. Those are 2x values. So we're going to get a negative here popping out, a negative h, and we're going to get negative root 3a over 2h. And so that's going to be our m. So we can plug in, h prime equals, now plugging in m, our slope, x plus b. Now again, we have to solve for b, our intercept. The easiest way to do that is just to plug in for when x equals 0. And when x equals 0, h equals root 3a over 2 equals negative root 3a over 2h times 0. So this term is going to go away, plus b. So b equals root 3a over 2. So we end up with our equation of line, h prime, now that we know our slope and our intercept, equals negative root 3a over 2h x plus root 3a over 2. Great. So we've done a lot of actually the hard work, and now we can just sub these in. So I'm gonna write this equation up here again, just so we can have this preserved while I erase and make more space. But at this point, we're just gonna have to sub these in. to our equation, and we'll be pretty much home free to be able to do some integration. So we got everything in the right form, everything's as going to be as a function of x now. So that's nice. Okay. So sorry for the delay here. Let's really give ourselves a lot of space. So what this is going to do, again, remember this is we're all in terms of a generic tetrahedron here, the generic H. That's what we're doing first, and then we'll go to the regular tetrahedron because we're going to a generic H value. All right, so let's plug this in now. 1/2 and B prime was negative A over HX plus A. And then H prime was negative √3A over 2HX plus √3A over 2. And all that was times dx. So what you can see here is we have a FOIL situation where we have to go first outside, inside last. And so I'm going to continue over here. And so this is now just a bunch of algebra and then integration. But we can do it together. So we're going to end up with we're gonna end up with negative A over 2H x plus A over 2. Here I'm just factoring out the 1/2. I think that's probably the clearest thing to do. Here, let me just make this a little more clear. Negative A, okay. And just rewriting this part. Yeah. So now let's FOIL. And so this ends up foiling as, let's see, I think I'm probably going to need more room. It's hard when you have long mathematical expressions. So we're going to go down here, give ourselves the maximum amount of room. So first, we're going to get, we have 2 negatives, so that's going to give us a positive value, √3a squared, a times a, over 4h squared, x squared. And then we can do this one, this term, let's say times that term. That's going to get us negative √3a squared over 4hx. And then if we do the other term, so let's see, that would be this term times this term. We actually get the same thing. Negative √3a squared over 4h. And then the last terms, we get positive √3 a squared over 4. So there's no h in that part. And all this, again, is times by dx. Nice thing about this is that we have common terms here. So let's combine. So we still have √3a squared 4h squared x squared, but we have √3 over 4 minus √3 over 4, so that's going to be minus √3 over 2 a squared. Sorry, I forgot an x here. Yes, just forgot the x there. But anyway, those are the same terms. So that's why we're able to combine them. So we have an x here, and then this last term, we don't do anything to yet. All right, we're almost home free. So now we have, we can separate this into 3 integrals, right? And so I think at this point, I'm going to just go to the next page and totally give us some more space. So just to write what we had before, but separating it out into 3 integrals, okay? Because we had minuses or plus signs, separating them, so we can separate this into 3 integrals now. It was integral 0 to h root 3 a squared 4h squared x squared dx minus, now another integral, 0 to h root 3 a squared 2h over x dx. Those are the terms we combined, and then this was the last one that just had the integral of a constant, which is root 3 a squared over 4 dx. And now that we have everything looking pretty nice, we can pull out the constants and start to actually integrate this stuff. So our constants are root 3 a squared over 4h squared. Let's go ahead and now actually integrate. So I'll use the straight line notation. The integral of x squared dx, of course, is 1/3 x cubed. So the derivative of 1/3 x cubed is x squared. And then we have a minus sign, and we'll pull out that constant, root 3 a squared over 2h. Line notation from 0 to h. Integral of x is, of course, 1/2 x squared. And then our last part, again, we have a constant pull out here, is just integral dx, which is x. And so now, all of our hard work starts to pay off. And we've got 1/3 h cubed minus 1/3 times 0 cubed, which of course is 0. And we're then going to have something a little bit similar on this side equation, 1/2 h squared minus 1/2 0 squared. So that part's going to cancel out. And this is going to be root 3 a squared over 4 times h minus 0, which is going to be h. So we get all this, getting rid of the 0 terms here. Now we're going to have root 3 and a 3 times a 4. So we're going to have a 12 on the bottom of h cubed. This term goes away. These terms all go away. The 0 terms. So we got h cubed divided by h squared. So it gives us an h on the top. And this part, we're going to have an a squared. And we have a half times a 2 on the bottom. So that gets us a 4, and h squared on the top divided by an h. That gets us an h. Okay, and lastly, we have this term, which is just root 3 a squared h over 4. So these terms cancel out because they're the same. One's a negative, one's a positive. So we end up with root 3 a squared h over 12. And that's actually our final answer, our volume. So this is for, a non-regular, tetrahedron. We use calculus for a tetrahedron with an arbitrary height h. H. And an edge of that bottom triangle of A. Okay, so at this point, let's take this formula and go a step further. And so I'm gonna rewrite this formula at the top for us. That was root 3a squared. Let's do it now for a regular tetrahedron. So this part doesn't really have any calculus now that we did the generic formula. All we have to do is figure out what H is for a regular tetrahedron. And so the way to think about this is that, well, we need to figure out the height of this guy when it's regular. And so when we draw down a height, we are going to be drawing height going down to the center of this base triangle. And so that's the starting point. And so what we first have to do is let's just draw that equilateral triangle on the bottom. This is the base. And we're trying to figure out essentially this triangle I'll draw it in red. We're going to need this triangle. This is a right triangle. And one of the sides is this line here. We know that has A by definition. So if we're to draw that red triangle on side view, right? Same red triangle there. This we know as A. This is H, but what is this, right? That's what we have to figure out next, okay? And so we know that this is coming to the center of that base triangle. And so let's call that, I'm going to call that length there D. Call it D here. Call it D. And we know that this is a 60-degree triangle, 60, 60, 60, and we're bisecting this angle. So this is a 30-degree angle. And we're coming down, and we're going to come down here. And the interesting thing about this triangle is that, anytime we draw a line here, it's coming on a 30-degree angle, we're cutting this length of the edge in two. So this length right here from here to there is going to be A over 2. And so that allows us to now figure out what D is. We can just do cosine of 30, right, equals adjacent over hypotenuse. Cosine of 30 equals A over 2, and then over our hypotenuse, or cosine rules, which is what we call D. It's going to be A over 2D. Cosine of 30, you may remember, is root 3 over 2. And so now we can solve for D. Root 3 over 2 equals that. And so when we end up doing that, we get D equals A over root 3. The 2's and end up canceling. And so now we actually know, instead of putting D here, we can say, hey, this is actually root 3, A over root 3. That allows us now to use the Pythagorean theorem to figure out what H is, which is our height of our regular tetrahedron. So again, no calculus here. This is just, a bunch of geometry. There's a lot of different ways you can figure this out, but this is just the way I like to do it. Or at least decided to do it here. So A squared plus B squared equals C squared. There's the hypotenuse. The hypotenuse is A here, so the C squared. So H squared plus A squared over 3, right? A over root 3 squared equals A squared, the hypotenuse. And so H squared actually equals 2/3 of A squared. So then taking the square root of that, we get root 2A over root 3. We can clean that up a bit, n times by root 3 over root 3. and figure out that the height is root 6a over 3. So at this point, we're pretty much home free. We just have to plug in this h, because we know when we have a regular tetrahedron, the height is root 6a over 3. So we plug it into our original generic formula for a tetrahedron with any arbitrary height. And we're going to get the h times h, so it's root 6a times 3. So that's going to equal root 18 a cubed over 36. We can pull out a 9. 18 is 9 times 2, and a root 9 is 3. So we're going to end up with pulling out a 3 there and a root 2. And we're going to end up with a cubed over 36. And so that ends up getting us root 2a cubed over 12. And if we want to times that by root 2 over root 2, we'll get our final formula for a regular tetrahedron, which is a squared over 6 over root 3. Basically because we have 2 12ths there, so we got 1/6. That's our volume of a regular tetrahedron. And the only thing you have to define there is the length of the edge, because all the faces are the same. And you don't even need to know the height, because we figured out what the height was in terms of A. So I hope you enjoyed this derivation. Using calculus, you can determine the volume of many different types of shapes.